When implementing a deep neural network, one of the debugging tools I often use to check the correctness of my code is to pull a piece of paper and just work through the dimensions of the matrix I'm working with. So let me show you how to do that, since I hope this will make it easier for you to implement your deep nets as well. So capital L is equal to 5. Right? Count down quickly, not counting the input layer. There are 5 layers here, so 4 hidden layers and 1 output layer. And so if you implement forward propagation, the first step will be Z1 equals W1 times the input features X plus B1. So let's ignore the bias terms B for now and focus on the parameters W. Now this first hidden layer has 3 hidden units. So this is layer 0, layer 1, layer 2, layer 3, layer 4, and layer 5. So using the notation we had from the previous video, we have that N1, which is the number of hidden units in layer 1, is equal to 3. And here we would have that N2 is equal to 5, N3 is equal to 4, N4 is equal to 2, and N5 is equal to 1. And so far we've only seen neural networks with a single output unit, but later, in later courses, we'll talk about neural networks with multiple output units as well. And finally, for the input layer, we also have N0 equals Nx is equal to 2. So now let's think about the dimensions of Z, W, and X. Z is the vector of activations for this first hidden layer. So Z is going to be 3 by 1. It's going to be a 3-dimensional vector. So I'm going to write it as a n1 by 1 dimensional vector, or n1 by 1 dimensional matrix. Right? It's 3 by 1 in this case. Now, how about the input features X? X, we have 2 input features. So X is, in this example, 2 by 1. But more generally, it will be n0 by 1. So what we need is for the matrix W1 to be something that when we multiply an n0 by 1 vector to it, we get an n1 by 1 vector. Right? So you have sort of a 3-dimensional vector equals something times a 2-dimensional vector. And so by the rules of matrix multiplication, this has got to be a 3 by 2 matrix. Right? Because the 3 by 2 matrix times a 2 by 1 matrix, or times a 2 by 1 vector, that gives you a 3 by 1 vector. And more generally, this is going to be an n1 by n0 dimensional matrix. So what we figured out here is that the dimensions of W1 has to be n1 by n0. And more generally, the dimensions of WL must be NL by NL minus 1. So for example, the dimensions of W2, for this, it will have to be 5 by 3, or it will be N2 by N1, because we're going to compute Z2 as W2 times A1, and again, let's ignore the bias for now. But so this is going to be 3 by 1, and we need this to be 5 by 1, and so this had better be 5 by 3. And similarly, W3 is really the dimension of the next layer, comma, the dimension of the previous layer. So this is going to be 4 by 5. W4 is going to be 2 by 4, and W5 is going to be 1 by 2. Okay? So the general formula to check is that when you're implementing the matrix for a layer L, that the dimension of that matrix be NL by NL minus 1. Now, let's think about the dimension of this vector B. This is going to be a 3 by 1 vector, So you have to add that to another 3 by 1 vector in order to get a 3 by 1 vector as the output. Or in this example, you need to add this, which is going to be 5 by 1. So it's going to be another 5 by 1 vector in order for the sum of these two things that I have in the boxes to be itself a 5 by 1 vector. So the more general rule is that in the example on the left, B1 is N1 by 1, right? That's 3 by 1. And in the second example, it is this is N2 by 1. And so the more general case is that BL should be NL by 1 dimensional. So hopefully these two equations help you to double check that the dimensions of your matrices W as well as of your vectors B are the correct dimensions. And of course, if you're implementing backpropagation, then the dimensions of dW should be the same as the dimension of W. So dW should be the same dimension as W, and dB should be the same dimension as B. Now, the other key set of quantities whose dimensions to check are these Z, X, as well as A of L, which we didn't talk too much about here, but because Z of L is equal to G of A of L applied element-wise, then Z and A should have the same dimension in these types of networks. Now, let's see what happens when you have a vectorized implementation that looks at multiple examples at a time. Even for a vectorized implementation, of course, the dimensions of W, B, dW, and dB will stay the same, but the dimensions of Z, A, as well as X will change a bit in your vectorized implementation. So previously, we had Z1 equals W1 times X plus B1, where this was N1 by 1, this was N1 by N0, X was N0 by 1, and B was N1 by 1. Now, in a vectorized implementation, you would have Z1 equals W1 times X plus B1, where now Z1 is obtained by taking the Z1s for the individual example, so that's Z11, Z12, up to Z1M, and stacking them as follows, and this gives you Z1. So the dimension of Z1 is that instead of being N1 by 1, it ends up being N1 by M, if M is the size of your training set. The dimensions of W1 stays the same, so it's still N1 by N0. And X, instead of being N0 by 1, is now all your training examples stacked horizontally. So it's now N0 by M. And so you notice that when you take a N1 by N0 matrix and multiply that by an N0 by M matrix, that together they actually give you an N1 by M dimensional matrix as expected. Now the final detail is that B1 is still N1 by 1, but when you take this and add it to B, then through Python broadcasting, this will get duplicated into an N1 by M matrix and then added element-wise. So on the previous slide, we talked about the dimensions of W, B, dW, and dB. Here, what we see is that whereas ZL, as well as AL, are of dimension NL by 1, we have now instead that capital ZL, as well as capital AL, are NL by M. And the special case of this is when L is equal to 0, in which case A0, which is equal to just your training set input features X, is going to be equal to N0 by M as expected. And of course, when you're implementing this in backpropagation, we'll see later you end up computing dz as well as dA, and so these will of course have the same dimension as z and a. So I hope the little exercise went through helps clarify the dimensions of the various matrices you'll be working with. When you implement backpropagation for a deep neural network, so long as you work through your code and make sure that all the matrices dimensions are consistent, that will usually help go some ways toward eliminating some class of possible bugs. So I hope that exercise for figuring out the dimensions of the various matrices you'll be working with is helpful. When you implement a deep neural network, if you keep straight the dimensions of these various matrices and vectors you're working with, hopefully that'll help you eliminate some class of possible bugs. It certainly helps me get my code right. So next, we've now seen some of the mechanics of how to do certainly forward propagation in a neural network. But why are deep neural networks so effective, and why do they do better than shallow representations? Let's spend a few minutes in the next video to discuss that.